Hello all. This is about my recent work, admission control for hierarchical inference offloading with a single server queuing system. Our work focuses on designing a policy that maximizes the overall system performance by maintaining queue stability. You might be thinking about what system am I talking about and what is queue? What does queue stability even mean? Now let's discuss everything in detail. We considered a system with edge devices and an edge server. Edge devices are the devices which we utilize daily. Some examples of such devices are laptops, mobile phones, IoT devices such as Raspberry Pi, and personal computers. Edge server is a remote server which is somewhere near to the devices, accessible only through a wireless link. Now we are using this system to perform image classifications. Images are the tasks arrive to each device uniformly at random. To classify such images, we deployed a pre-trained ML model on each device and on the edge server. As edge server has abundant access to power, memory, and compute resources, we deploy the state-of-art model that takes the advantage of such available resources and produce best accuracy known so far. As the devices doesn't have access to such resources, we deploy smaller model that utilizes less resources with compromised accuracy. Now, once a task is fed to an ML model, it classifies the tasks with some confidence score. This confidence score is a measure of the model confidence on the current task classification. We first analyze the simpler version of the earlier system in which only one edge device and edge server are present. In this setup, if you observe, when the device is fed with an image of a dog, it predicted the image as cat and with some confidence score, which is 0.54. Now, if this output is given to the user who is observing the device so far, the overall system accuracy drops. But the ground truth is not known in general. Here, since for the explanation, I just told that the image belonged to a dog. What if there is no such, you cannot observe the ground truth, which is the usual case when an user perceives the given task. Now, in such a case, one need to design a policy to maximize the system accuracy. As confidence scores are the measure of system model confidence, our policy uses these scores to perform task inference effectively. Now, for any given task, our policy uses the confidence values and chooses a threshold using the prediction with expert advice with experts as the set of thresholds so far which were chosen at random, and decides and takes the offloading decision which is to offload or not. Now once it decides the tasks to be offloaded, uh, it offloads the given task into an offload queue, which you can observe. The dog image is actually fed into, the dog image is actually fed into the task queue, offload queue. Now the tasks in this offload queue are then transmitted to the server and then served according to the queue policy. Now, due to the time constraints, I am not going into the details. You may see our paper for further clarification and explanation. Now, if you observe, in general, this server is usually connected to many such devices. So we used time division multiple access where it serves in order to, so it might have to, like, share the resource, share its resources with the existing devices so far. So we, in order to mimic the time division multiple access, we say that this upon the tasks arrived, or upon the tasks that are in offload queue, the server serves each task with some probability, with some service probability. Now, okay, when implemented our policy on the system, we observed that the queue length of the offload queue remained the same for every service and arrival probabilities observed so far. And as the system accuracy is depending on the service probability of the server, because once if we observe that the task, if the device observes that the confidence is not up to the value, it starts to offload it to the queue, and the task just sits waiting for the server to be serviced. And now if the service rate of the if the service probability of the server is high enough, then such tasks are serviced, thereby increasing the overall system accuracy. If not, the tasks will just remain at the queue, and then the queue might get cluttered up, so that thereby reducing the overall accuracy of the system. That is what we observed in our simulation as well. For service probability 0.001, we observed that the maximum accuracy we can achieve is 40%. Whereas if the service probability is 0.05, you can achieve at most, like 100%, almost 100% accuracy. And as soon as the arrival probability keep on increasing, I mean the more tasks being arrived to the system, the accuracy plummeted, which is because uh, if all such tasks if are added to the queue, thereby the queue stability, the queue might be unstable. So in order to maintain queue stability as well, we start to accept more tasks in order to reduce the queue offloading, task offloading to the queue. So so these are our results, and thank you.